Welcome! In this video, we explain the autotuning of induction motors and how the electrical parameters for the equivalent circuit are accurately determined. Here we see the classic T-equivalent circuit of one phase of the induction machine. To model the behavior precisely, 5 core parameters must be determined. These include the stator resistance and stator leakage shown in blue. In the center, the mutual inductance LH branches off in yellow, representing the magnetic field in the air gap. On the purple rotor side, we have the rotor leakage and the load-dependent rotor resistance. Parameter identification begins at standstill. This is advantageous because the load can remain coupled. First, the DC measurement is performed. Next, the inverter injects a high-frequency single-phase AC voltage. Due to the high frequency, the motor does not rotate. The total leakage inductance is calculated from the reactance. A rotational measurement is necessary for the precise determination of the mutual inductance LH. The motor runs up without load. At no load, the current drawn corresponds almost entirely to the magnetizing current, from which LH is directly determined. During the rotational measurement, the inverter varies the magnetizing current step by step. The Froehlich model describes the physical saturation of the iron. Alpha corresponds to the reciprocal of the unsaturated mutual inductance, while beta represents the maximum saturation flux. By taking the reciprocal, the relationship becomes linear, enabling a resource-efficient least squares regression directly on the microcontroller. In doing so, the limits of the magnetizing current must be strictly observed. Too high a current drives the machine into oversaturation, causing the mutual inductance to collapse and the tuning to abort numerically. Conversely, too low a current leads to noisy measurements and incomplete saturation capture, causing control instabilities during operation. In summary, field-oriented control can be activated right after the standstill measurement. The rotational measurement is optional and increases precision by capturing the mutual inductance and the saturation curve. The rotor time constant tau determines how quickly the rotor flux decays during coast-down. The inverter preferably determines this value via a coast-down measurement. By blocking the pulses while the motor is spinning, the exponential decay of the induced stator voltage is measured. This is temperature-independent and shock-free for catch-on-fly. Alternatively, tau can be calculated using the classic equation from mutual inductance and rotor resistance, serving as a fallback. Since the magnetic rotor flux, due to the small rotor time constant, decays much faster than the mechanical coast-down of the motor takes, the catch-on-fly function uses two methods. EMF tracking utilizes the remaining rotor remnants and catches the motor extremely fast by passively measuring the frequency and phase of the induced stator voltage. If the field has already completely decayed, the slower frequency sweep is used. Here, a small test current is injected and the speed is actively identified via the voltage drop. Thank you for watching.